Welcome to University of Alberta's International Week 2025. I'm Amit Kumar. I'm a professor in mechanical engineering here at University of Alberta. I'm also Canada Research Chair in Assessment of Energy Systems. And a lot of focus is on working on different pathways for mitigation of greenhouse gases. And we'll get into it a little bit later on. I'm so happy to be with you in this session. I would first like to do our land acknowledgement. So the University of Alberta acknowledges that we are located on the traditional Treaty of Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, and Ozabe, Saltu, Anishinaabe nations, lands that are now known as part of Treaties 6, 7, and 8, and homeland of the Métis. The university respects the sovereignty, lands, histories, languages, knowledge systems and cultures of First Nations, Métis, Inuit nations, whose presence continues to enrich our vibrant community. So for 39 years, International Week has provided a forum to share ideas, inspire discussions, and animate debates on current global issues and the solutions required to create a better world. And we'll be talking about one of these issues today. So before we get started, here is an outline of how today's session will go. For the question and answer portion of our event, we'll display a short URL, menti.com, an 8-digit code on the screen. If you'd like to submit questions, please go to menti.com. From any device and input the 8-digit code to do so. You do not need an app or an account. Just a website would be good. Our behind-the-scenes moderator will receive your questions and put them in the queue for me to ask our speakers as time allows. Along with me, I have Matthew Davis. He's a PhD student in my research group. I'll invite him to give a bit of information on his work and his background.
Yeah, so hello everyone, happy to be here. So my research focuses mainly in the area of energy systems modeling, machine learning, and future energy systems. So I spend quite a bit of time developing methods of how we model energy systems, and then developing models and running experiments with those models. So we can look at going into the future, kind of how we can transition our energy systems to be more sustainable, less costly, and in the end, try to reach some of the climate targets that we have to meet.
Good, Matt. I mean, that's one of the key issues that world is facing today. So today we'll be talking about future energy generation. To discuss about future energy generation, we need to understand our current energy utilization and generation. If you see today, almost 82% of our energy comes from fossil fuels. And when I refer to fossil fuels, it includes coal, oil, natural gas. And if you see how this has increased dramatically from 2005 to 2022, almost 26%. So that's a huge increase. If you look at the total energy consumption, in fact, over this time period, it has also increased by 26%. So very much a direct correlation between the fossil fuel use and also in terms of the population. So if you look at the population, currently we are around 8 billion people in the world. In 2005, it was about 6.6 billion. So again, a 26% increase. So a direct correlation between energy use and the population increase. The other key aspect about this fossil fuel energy utilization is, if you look at globally, there are only 21 countries which produce energy, fossil fuel. Majority of the energy is produced by only 21 countries around the world. And if you think about it, we have about 193 countries in the world. So it's very concentrated in terms of where it is available. If you look at coal, for example, only 4 countries in the world, they produce about 75% of the coal. If you look at oil production, only 6 countries in the world produce almost 60% of the oil. Canada is one of them. And if you look at natural gas, another major fossil fuel, again, 60% of this energy globally is produced by 7 countries. Canada is one of them. So it's very concentrated, and Canada is one of the key countries producing these natural resources. I should also mention that any of these fossil fuel that we use is associated with emission of greenhouse gases. And that would be one of the key things also we will be discussing today, because it leads to global warming. And our GHG emissions have increased almost 22% over a period of from 2005 to 2022. So we'll be talking about more in terms of the future energy generation, its environmental impacts. The future energy generation will depend on population, the associated demand of energy, how much energy the people use, what countries have to support this energy demand. Either they are an importer or they are an exporter. It will also depend on geopolitical situation in terms of the energy trade from one jurisdiction to another jurisdiction, and then the need for GHG mitigation. So all of these, if you think about the production of energy and then its environmental impact, basically is part of and the impact of an energy system. So let's just first try to understand what an energy system is at a very high level. And at this time, I would invite Matt to basically give us a little bit of overview of what actually an energy system means, what it consists of, and then what are the environmental impacts of an energy system. Matt?
Yeah, so I mean, energy systems are basically made up of everything around us that consumes, produces, transports, and stores energy. And these things are all connected through energy networks as well. So just for example, I mean, this building that we're in is part of the energy system. So these lights that are consuming electricity right now, from the energy systems perspective, we would ask, so where is this energy coming from? So we can trace this energy back from the lights, back to the electrical grid, which is an energy system within itself. And that electrical grid is connected to electricity generation plants. So we have power plants generating energy. And in Alberta here, it's mostly based on natural gas power. So those power plants will be using natural gas. So then we'd also ask, so where's this natural gas coming from? So then we can trace that back through natural gas pipeline systems, possibly underground storage, through natural gas processing plants, and ultimately back underground where we extract that resource in the first place. So energy systems is really the study of where does your energy come from, how we use it, how we store it, how we transport it, and also going into the future, how do we make that more sustainable?
Yeah, that's excellent, Matt. I mean, you talked about the energy system and then the different unit operations that it includes. So, all the way from production, transportation, then again conversion to secondary energy, then transportation of that energy, and then the utilization piece. And as you alluded, like all of these unit operations, if you think about, in terms of natural gas or in terms of any other energy source, each of these unit operations have environmental impacts associated with it.
Yeah.
More in some cases when you do, for example, fossil fuels, so more GHG emissions, and then in case of the renewables, it's less. But all of these unit operations in the whole energy system, if you do any changes, it has a GHG emission associated with it.
Yeah. So GHG emissions are a major issue kind of that we're tackling right now. So the world's energy use is all currently based on about 80% fossil fuel. So about 80% of the world's energy comes from fossil fuel. And when we use these fuels for energy, we produce carbon dioxide and other greenhouse gas emissions. And these basically trap heat in the atmosphere and in the oceans. And this is having some kind of dangerous impacts on climate. I mean, right now, we've released so much greenhouse gases that the concentration of CO2 in the atmosphere is currently over 420 parts per million. And if you look back through history, this is the highest level it's been in about 14 million years. So the total amount that we released is an issue, but also the rate that we've released it is also an issue. So if we do look back to the last ice age, when we were going through a warming period, about 20,000 years ago, carbon dioxide concentration increased by about 80 parts per million over 6,000 years. And just in the last 40 years, we have achieved that 80 parts per million increase. So, and this is what's leading to some significant instability in the climate.
Right, and I think like GHG emission is a big issue, and there has been a lot of international treaties and collaborations to reduce these GHG emissions. You look at the most recent one is like it started all the way from Kyoto Protocol, then you had the Paris Agreement, where countries have tried to pledge in terms of how they're going to reduce the GHG emissions and the support for this. Let's talk a little bit about, we talked about energy system, the associated impact, and GHG emission is a key aspect of it. What are the pathways how we can mitigate greenhouse gases? Could you talk a little bit about those baskets of options?
Yeah, so I mean, there are lots of options how we can reduce greenhouse gas emissions. Broadly, we can probably categorize them into 3 different baskets of options. So the first would be energy efficiency. So this is basically reducing the amount of energy that we need to consume to provide some energy service. So for example, if we switch from driving gasoline vehicle to electric vehicle, we're actually going to use 3 to 4 times less energy to drive the same distance. So that's an example of energy efficiency. Another example of energy efficiency would just be using better materials when we construct buildings and homes. Those materials might trap heat more effectively, so we have to use less heating energy to heat our homes and our buildings. The second category would be alternative energy sources or fuel switching. So for example, if we have electricity generation using natural gas power plant or a coal power plant in our electricity sector, we can transition to low carbon or zero carbon sources of energy and electricity. So more wind, more solar, even nuclear power. The third option broadly is carbon capture and storage. So if we have our coal power plant, instead of releasing all of the emissions to the atmosphere, we'll actually capture those and store them underground permanently. So then we avoid the greenhouse gas emissions to the atmosphere.
No, I mean, I think, those are the 3 broad baskets. And I think, in terms of the 3 baskets that you talked about, I mean, each of these different demand sectors have a role to play in that, right? In energy efficiency, residential sector, but you have industrial sector where you're going to improve the efficiency. Transportation you talked about, agricultural sector, forestry sector, all of these can improve their efficiency. And I think the energy efficiency is one of the most low-hanging fruit. So it's basically the low-cost option that you could do. But one of the challenges with energy efficiency is also that there is a limit how much you can mitigate.
Exactly.
And potentially for Alberta, some of the work that we have done, about what, 24 million tons that you can mitigate. And that could go probably, you could plus or minus, but there is a limit how much you can mitigate. And then you have to look at the other 2 baskets that you talked about. I would also add in terms of carbon capture and storage. So we talk a lot about capturing CO2, which is produced, like say coal or natural gas plant through flue gas, separate the CO2, put it underground. But there is also another basket of option which is coming up where people talk about carbon dioxide removal technologies. So these are basically you can implement anywhere. You extract CO2 from air. And this is like, direct air capture is one of the technologies. But, in the renewable option, we talk about bioenergy as a source, a renewable source of energy because it is inherently carbon neutral over its life cycle. Because when you burn wood chips or a straw, the CO2 that you emit, basically that is taken up by the plant when it grows. So it's kind of over the life cycle, it's carbon neutral. But what they talk about now, there is a lot of emphasis on adding carbon capture and storage to these bioenergy generation. So they call it BECCS, so bioenergy with carbon capture and storage, and this is also one of the pathways for carbon dioxide removal technologies. And there is also focus on enhanced mineralization where you basically sequester CO2 through forming minerals. So I mean the carbon capture and storage basket is expanded, and my sense is that is a key basket to mitigate greenhouse gases. I would also add in terms of, so you talked about 3 baskets. There's also, we are like, now working a lot on looking at hydrogen. And I put hydrogen in both the baskets. So you have renewables because you can produce hydrogen from renewables through electrolysis and then water as a feedstock, splitting water through the renewable electricity, producing hydrogen and oxygen. But we can also produce hydrogen through natural gas. and then with carbon capture and storage to produce low carbon intensity hydrogen.
Yeah.
So, I mean, hydrogen is another option. Maybe we should discuss a little bit more in terms of the hydrogen and what it could do, because that is one of the pathways which can help in mitigating greenhouse gases significantly.
Yeah.
I mean, if you look at hydrogen, hydrogen is one of the lightest elements in the universe. It is most abundant next to helium.
Yeah.
And it is, if you look at hydrogen, it's colorless, tasteless, odorless. And you can burn it. When it burns, it produces water. Mm-hmm. So that's kind of very benign in terms of, what hydrogen could do. It's part of vast quantities like in water, oceans, liver, all of them have hydrogen in form of water. So the potential is large. Like currently, if you see where we use hydrogen, most of these is used in upgraders. For example, in Alberta, we have bitumen. We produce a lot of bitumen. So we add hydrogen to bitumen to produce synthetic crude oil. So all of these upgraders here has a hydrogen production unit, and they produce hydrogen from natural gas, and the process is called steam methane reforming. So they produce hydrogen but use it continuously. And currently, they don't capture the CO2 which is emitted during the production of hydrogen. So, we term it as gray hydrogen. But if you add carbon capture and storage to it, then it is called blue hydrogen because the carbon intensity goes down. We also look at hydrogen production from renewables, as I mentioned. So any renewable electricity that you have, so either it is from wind, solar, hydro, biomass, all of these can be used in an electrolyzer and water as a feedstock in an electrolyzer, separating water into hydrogen and oxygen, so producing hydrogen. So those are called green hydrogen.
Yeah, and green hydrogen can be a key enabler for renewable-based technologies like wind and solar.
Right.
So one disadvantage of wind and solar is that we can't control when they output electricity. Mm-hmm. So when we're looking at future energy systems and we produce a lot of electricity from wind and solar, maybe the demand for electricity isn't matching with the generation from those technologies. So using hydrogen, in the periods where we have lots of electricity being supplied, but we don't have enough demand to consume it, instead of basically turning those plants off, we can produce cheaper hydrogen from that excess electricity and store that hydrogen for use in various applications throughout the economy.
Yeah, and that's an excellent point. I mean, hydrogen can be a form of energy storage, right? So you can store these renewable electricity in the form of hydrogen and then use it when you don't have wind and solar.
Yeah.
The other advantage is also that it allows you to transport that renewable electricity. So if you want to transport from Canada all the way to Europe, your renewable electricity, hydrogen provides a medium, how you can convert these renewable electricity using water to hydrogen and then transport from one continent to another continent. Yeah. I mean, there is a lot of talk about transporting hydrogen from Canada, either it's blue hydrogen or green hydrogen, to different places in the world, Asia Pacific countries or Europe. So it provides that option. Yeah. It is also interesting to see because we have been using hydrogen for a long time in the refineries, even for our oil sands sector, in also producing ammonia, and for fertilizers. So we have been using hydrogen, but there is a lot of talk now on using hydrogen. Predominantly, the focus is more on using in other demand sectors. Yep. So you have industrial sector where the high temperature applications, there are not a lot of decarbonization pathways. So you could use hydrogen. Wherever you use hydrogen, wherever you use natural gas as a heat source, you can use hydrogen. Yeah. So now there is a focus a lot on in terms of where you can use hydrogen in other sectors, demand sector, transport sectors, industrial sectors. So that is also, again, a key benefit. The other aspect that I think, and maybe you could talk a little bit about it, is is there a big potential for hydrogen in Alberta? What makes Alberta as a leader in hydrogen?
Yeah, so Alberta has really abundant and low-cost natural gas that's available. And of course, natural gas is a fossil fuel, so when we use it for energy, we do emit greenhouse gas emissions. But one thing we can do is convert it to hydrogen and basically use that hydrogen anywhere that we're currently using natural gas. So for example, most homes and buildings are heated in Alberta with natural gas. You have natural gas furnaces and boilers. But we can convert that natural gas to hydrogen and use that hydrogen to provide heat in our homes, in buildings, for cooking, basically anywhere you use natural gas. There's also opportunity to use it in the transportation sector. So when we're looking at very long haul, heavy duty freight, hydrogen is quite advantageous there compared to battery electric technologies, for example. And so Alberta also has a lot of natural gas infrastructure that can be used with hydrogen. And also our workforce is trained and experienced in handling natural gas systems, and also production of hydrogen already. So Alberta is already a global leader when it comes to producing and using hydrogen. So I think all of those together, you kind of really put Alberta ahead in terms of experience and technology development for hydrogen.
Yeah, and I think, I'll add one more point, is that we have so much of natural gas, but we also have carbon capture and storage infrastructure.
Yes.
The Alberta Carbon Trunk Line, which is a 14 million ton per year capacity.
Yeah.
So you can basically produce hydrogen using natural gas through SMR or the new technology in terms of autothermal reforming, and then capture that CO2 and put it underground in Alberta.
Yeah.
And the best part about Alberta is also that our geology is such that you can sequester CO2. This is not available around the world. So if you think about all the ingredients for a successful hydrogen economy, you have the resources, you have the know-how how to produce hydrogen on a large scale. So we have been producing a 350,000 tons a year plant, which is such a large plant, over decades. So we have the know-how, we have the workforce, trained workforce, we have the geology to sequester CO2 so that we can produce low carbon intensity hydrogen. So, all of these factors actually make Alberta a leader. So, and that's a big potential for us.
Yes, yeah, I think a lot of rare things that other places around the world wouldn't have, kind of all have come together in Alberta,
right,
in particular for hydrogen, yeah.
Good, good. So we talked about, energy systems, the impacts of energy systems. We talked about the different baskets of options. We talked about hydrogen. There is a lot of also focus on nuclear.
Yeah.
And the potential for nuclear to help in decarbonization globally.
Yeah.
So could you talk about nuclear and then the pathway forward with nuclear?
Yeah, so nuclear isn't really featured at the same level of renewable technologies like wind and solar, but nuclear really will be a key technology, especially if we have to eliminate virtually all of our greenhouse gas emissions, because it's a reliable source of heat and electricity. It's a mature technology, but unfortunately the public perception is quite negative, and so I think that's why you don't see as much talk about nuclear, and that's because we've had some serious accidents in the past for nuclear plants. But actually, when you look historically at all of the nuclear accidents and maybe the safety profile of other sources of technology as well for energy, you actually find that nuclear energy is quite safe, kind of comparable to how safe solar power is. When you look at health impacts and fatalities per unit of energy produced, nuclear is actually quite safe, and modern technology, does not have the issues that we faced in the past with those nuclear disasters. So nuclear would be a key piece because it emits zero carbon, and you can produce very, very large quantities of energy, both heat and electricity. And now, we're developing kind of next generation nuclear reactors, and these will be smaller plants. So right now we do face challenges with conventional nuclear power. So they're very capital cost intensive. They're relatively large plants, so they have a land footprint, and they're relatively inflexible as well. So once you turn them on, it's hard to kind of ramp them down, ramp them up to meet the demands. So the next generation technology is small modular nuclear reactors, and there's quite a bit of R&D going on in Canada for those. And those are meant to address a lot of the challenges that we have right now with conventional nuclear, and probably we'll see those be deployed at a quite large scale in the next 10, 20, 30 years into the future.
Yeah, good point. And I think nuclear has, and we have been doing it for decades. You have large-scale nuclear plant around the world and operating successfully.
In Canada as well.
In Canada as well. You look at large nuclear plants in Ontario.
Yep.
And small modular reactors are more decentralized, and these are units which are coming up, newer technology. So these are what, 300 megawatt units, which is kind of 1/3 of a large scale power plant, large scale nuclear. And small modular nuclear reactors have a lot of advantages in terms of, I mean, as I said, these are modular, so you can build parts in the factories, and then you can ship those parts and assemble where this is needed.
Yes.
Some of these other aspects is that, you know, the larger nuclear plants need 1 to 2 years of refueling, so you have to refuel them again every 1 to 2 years. These ones you could refill in 3 to 7 years, and people are working on where you have to refuel that every 30 years. So you don't even have to worry about refueling. So some of the key advantages which is there in terms of the small modular nuclear reactor. And I think now, with a lot of focus on other forms of energy, so small modular nuclear reactors, they're going to help you provide electricity, but also provide heat. And in fact, for our application here in Alberta, a lot of extraction of bitumen that we do through steam methane, so for the steam injection, the SAGD process, I mean, you could produce that is steam using nuclear heat and in a modular modular form. So I think there is a lot of advantages of a small modular nuclear reactor. And globally, my sense is that this will play a key role as we plan to decarbonize, because, as you said, there's not a GHG emission. There is the footprint of GHG emissions from nuclear is very low. It's almost near to zero. So good. And probably this, maybe we talk a little bit about, since we talked about the small modular nuclear reactor, we also kind of, we see there is also kind of, discussion on centralized and decentralized energy systems. Could you talk a little bit about and give some examples of centralized and decentralized energy systems?
Yeah, so for a centralized energy system, we're really talking about, for example, in the electricity sector, a very large scale power plant, which can provide electricity to, many different communities, many different industries throughout the province. So in a decentralized approach, we have generation and consumption very close together at a smaller scale. So for example, you might have a community that has solar photovoltaic electricity, generating and consuming their own electricity. So we see these actually all around Edmonton, and of course throughout Alberta as well. In Edmonton now, when you drive, you virtually will always see solar panels on some roofs. And just in the past 5 years, that's really, really ramped up. So that's an example of kind of decentralized energy. They're not consuming energy produced at a power plant far away, but they're just producing and consuming in a very close proximity. And there can be a lot of advantages that come with that. So we reduce the strain on the electrical grid from the centralized production plants. And also consumers can have more control over the electricity that they're consuming. And I think this is also probably a bigger deal in a lot of developing worlds.
That's right.
So where they don't have access to kind of large scale, low cost, centralized energy. And now they can kind of create their own mini grids in their local communities. And this has actually provided a lot of economic benefit for them.
And I think there are both pros and cons for centralized and decentralized system. I mean, a lot of our energy systems has developed. I mean, if you look at all these fossil fuel power plants are large centralized plants, thousands of megawatts. And one of the key driver for that has been is that the economy of scale for these plants. So I mean, typically, if you look at power plant and their economics, basically the capital cost per unit output goes down as you increase the size of the plant. So for a smaller plant, a decentralized plant, that capital cost per unit is higher compared to a larger plant. And that's why you see there has been a lot of drive for the centralized system. But then there are other advantages. Is in terms of, in a decentralized systems, you don't have to transport. You use the resource there. So for example, wind and solar, or solar basically, the photovoltaics which is at our home. Also, it also kind of, the transportation energy could be minimized because, if a country is net importer of energy, they get their, say, natural gas or oil from other countries, so it has to be transported. So transportation infrastructure needs to be there. So I mean, these are both pros and cons of centralized and decentralized system. Of course, there are some advantages in terms of having, local economy developed in the decentralized system. But the large plants also create a lot of construction jobs, a lot of operation jobs, these larger plants. So, depending on where you are, depending on whether you are a net importer of energy, net exporter of energy, what sources are available, the decision is more based on each and every jurisdiction, and it's particular to the jurisdiction. So good. I mean, we talked about a lot of topics here. Maybe at this time we might take some questions from the audience. And so there is one question here on how hard is it to convert our current natural gas distribution system to hydrogen? Can we distribute both? Or do we have to make a complete shift to be able to use our current infrastructure? Maybe I can start with this and you can add on. In terms of hydrogen transport, so you can blend hydrogen in a natural gas system up to 20% by volume. So you don't have to change the infrastructure. And that's kind of the blend is called hethane. So hydrogen plus methane. Natural gas is basically methane. And so up to 20% by volume, you can transport hydrogen in the existing pipeline. The moment you start going beyond 20%, then you have to change the infrastructure. You have to change the way you transport, so you have to change the pipeline. You have to change the equipment which uses that. So anything beyond that 20% by volume, you have to have the equipment which is specifically using higher amount of hydrogen. So for the existing infrastructure, hethane could be the start of the way how we start using hydrogen, 5%, 10%, 15%, 20%. But once you start developing the hydrogen communities which use 100% hydrogen for all of their energy use, you will have to have separate infrastructure, new infrastructure need to be developed which can use 100% hydrogen. Do you want to comment anything else?
I mean, I guess, minimal infrastructure changes when we're talking about blending hydrogen with natural gas. But when we're talking about transitioning from natural gas to hydrogen, then we need a lot of infrastructure development, both for hydrogen production, to produce it at scale for use where natural gas is used, for transport, so pipelining hydrogen from production to consumption, but also storage. So for example, if we had a hydrogen-based community where all of the homes are consuming hydrogen for space heating, water heating, cooking, then we would need additional infrastructure for storage to make sure that the supply of hydrogen would be reliable through the whole winter. So there's definitely a difference in the requirements for infrastructure depending on how large scale we go to adopt hydrogen.
That's right. Okay, good. There is another question here. This is an interesting one. It's on nuclear. So what are the storage issues of the waste? How is that waste managed? Does that get managed by the producer over the long term, or does the public take on the cost or responsibility?
Yeah, so waste is commonly talked about as a key challenge for nuclear power. Nuclear power, the industry is responsible for their waste. And when you look at the waste produced from nuclear power compared to conventional energy pathways like oil and gas and some other industries as well, nuclear is actually one of the only industries that takes care of their own waste. And actually, when you look at the amount of waste that's produced from nuclear versus these other industries, it's actually substantially less. So yes, it's maybe more dangerous from certain perspectives like radioactive and things like that, but we have ways to store this permanently, long term, forever basically, using engineered storage and so that there's no environmental impacts, there's no concern over the sheer amount of waste because it's actually quite a bit less than most people realize.
Yeah. Yep. No, and I think we have been doing it for ages, right? Large scale nuclear plants are there around the world, and they have been storing waste. We have the ways to store waste. We have the know-how how to store waste and safely. So I don't see that this is an issue. It's more about the public perception, but the large scale nuclear plants are there around the world, and they are building newer ones. But a good question. So we talked about, in terms of energy systems, the different options for mitigation, and then the associated issues. I want to get a little bit into terms of So for decision making, so in terms of, we talked about three baskets of options. So energy efficiency, that itself is thousands of options. We look at renewable energy, several different renewable energy sources, different technologies, carbon capture and storage, several pathways of carbon capture and storage, implementation of carbon capture and storage in different supply and demand sectors of energy. So when you have thousands and thousands of these options, the challenge comes in is that how do we choose?
Yeah.
And the question is in terms of, not only in terms of the people who use energy, it's both the perspective of energy importer and energy exporter. So in terms of importers, so for example, Germany, they have large manufacturing sector and they use a lot of energy which comes from outside. So their choice is more on, how do we choose this energy which can give me the mitigation that we desire. Exporter like Alberta, we produce energy for outside world. So our lot of challenges is in terms of the production of energy. So in terms of the oil sand systems, in terms of the natural gas system. So both it has the challenges in terms of the where we are looking at. Is it a jurisdiction which is a net energy importer or exporter? There are also challenges in terms of, we talked about thousands of these options. Basically the data sets. So what technologies are available? What are characteristics of these technologies? Some of these technologies are at very low technology readiness level. So it's still in developing stage. So you have either in the lab or the pilot scale. So actually characteristics of these energy, what is the emissions, what is the energy balance? Those are some of the key challenges in terms of deciding these different options. And sometimes these analyses are more, we look at either cost through techno-economic assessment, we look at emissions through life cycle assessment, but the challenge is in terms of how do we integrate these two in terms of making a decision. You also have challenges in terms of, a lot of these technologies are developed, but how will it penetrate into the market over a planning horizon of, let's say, 25 years, 30 years? We are in 2025. We want to reach net zero by 2050, so it's 25 years. How do we reach that? Like how this technology will penetrate different sectors? So there are challenges in terms of developing information related to that. Now we talked a lot about GHG emission, but there are other environmental impacts. Water is a big impact. And when we talk about renewable hydrogen production, water is in fact a feedstock. So jurisdictions where they have a lot of water, that's not a big challenge, but jurisdiction where there is a scarcity of water, green hydrogen might not be an option. So if you look at all these challenges, this seems very complex. And potentially there is everything that we can integrate and probably come up with some ways of assessing these options. So we talk a lot about integrated assessment. Could you talk a little bit about integrated assessment and the type of work that you are doing in helping the decision makers in this domain?
Yeah, I mean, this speaks to kind of the central research question of my PhD research, which is, considering all of those challenges and considering just the scope that we have here with the energy system. So all sectors throughout the entire economy, not just Alberta, not just Canada, but also other jurisdictions too. So we're connected to other places around the world just through our energy as well. So yeah, how do we combine all this together and produce some useful data for decision making? It's not like we have kind of a miniature scale planet to run experiments on. So basically what we do is we use computational models to simulate our energy systems. So we use mathematical representations of all of these systems. And so we simulate as close as we can to the real world how energy systems operate, what are the dependencies, how does one part of the system affect other parts of the system, so that we can use that to run experiments on. So for example, if we have technology A or technology B, and we need to make a decision, which path is the right path forward. So we can simulate if we make decision A within our energy system model, and we can measure all the impacts that might have over the next 10, 20, 30 years. So we might look at what are the water resource impacts, might look at what are the increases to energy costs. We want to minimize those as much as possible. And what is the impact on greenhouse gas emissions? What are the infrastructure requirements? What are the investment requirements? So by integrating all those together, we can produce a lot of data for one particular decision. What kind of effect will that have on our economy and on our energy system? And we provide that data as one part, but of course the policymakers which are making decisions, they have to weigh a lot more than just kind of the what data we would produce, based on environmental impacts and others. So they have social considerations, they have economic considerations, but we do provide those kind of hard data on what are the environmental impacts that this decision will have, what are the water resource, GHG, and what are the infrastructure impacts? And those are key metrics that they look for. Yeah.
Right, and I think these modeling, capacity, and then these models help you giving a trend in terms of what makes sense. Yeah. So then, at high level, and the impact over not only Edmonton, but at the provincial level or country level impact. Yeah. So you could basically bring all of these different options and their impacts on one page and look at these thousands of options and basically try to look at what gives you best bang for the buck. Yep. In terms of integrating the environmental impacts and the cost.
Yeah, we'll do a cost-benefit analysis on, maybe there is, like you said, there's thousands of options. If we're just looking at, a few primary options, we'll provide a detailed comparison, option A, option B, maybe even up to 1,000, on what is the cost-benefit of each of these decisions, so that we can try to balance all of the impacts and the trade-offs that might occur with each of the decisions. So.
No, and I think so modeling provides capability, and for us to, and the decision makers, basically how we take the data from a technology developer and transform it in a way that is used, that could be used by the decision makers for investment decision making or policy formulation. Right. Good, we have a couple of questions which have come in, so maybe we just discuss these. So the one question is on, have there been any successes in carbon capture and storage? And maybe I could comment on this is, there have been, and we have been doing it in Alberta. You look at the Quest project, we have been sequestering carbon. So we have been capturing carbon and then sequestering it underground. We already have large investment in terms of Alberta Carbon Trunk Line, which has the capability of transporting 14 million tons CO2 per year. So I think we are already doing it. We already have the infrastructure in place to do it on a larger scale. So this is already there. I'd go to another question here. How can a family in Alberta promote carbon capture in their own home? And if we can, will it be expensive, and will it make enough of a difference? Do you want to take that?
So it's a pretty complex question, and I don't know if there's an easy answer for it. I would say just education. So just know the facts and know, I guess, the potential for what the technology can do. I mean, there's pros and cons for it. So yes, we can implement a lot of carbon capture and storage throughout the economy and reduce emissions that way. But that would also likely increase the cost in certain areas. So, there's pros and cons to consider. So I think that looking at the facts, looking at that, yes, Alberta is a world leader when it comes to carbon capture and storage. So like you mentioned, we do have carbon capture and storage projects which have been going on for years already, successfully. And it looks like, that industry is going to grow in Alberta. But just like anything else, there's pros and cons. So
yeah, and to me, on a residential scale, potentially, carbon capture, when we talk about a lot of these carbon capture and storage technology, we're talking about more at utility scale, yep. Large scale, where there is large scale emission of carbon, yeah. So capturing that and putting it underground. But, as you said, in terms of support for this, at the residential and individual home level, the decarbonization options could be energy efficiency options. You look at a lot of these energy efficiency options in terms of how you use energy, so cooking, lighting, and you look at any of these appliances. So, those would be the key, I would say. And potentially, some of these decision making in terms of, probably installing solar panels in your house and using that energy. So those would be the decarbonization options. I think, with the time, we are reaching to the end of this. What I would like to do is, I'd like to talk a couple of minutes about the large scale initiatives in this area that we have at University of Alberta before we conclude. So, at the University of Alberta, we have a large group of researchers who are working on various aspects of decarbonization. One of the recent initiatives I would say is the Canadian Net Zero Energy Solutions. It's a large initiative. In fact, this is built on future energy system where we have about 200 researchers who are involved. We have near 2,000 graduate students and the researchers involved and trained in this process. That came through a large $75 million grant to the federal government. Now we are transitioning to this new initiative, which is the Canadian Net Energy Solutions. And here we are focusing on 5 major pillars. Hydrogen is one of them. We talked a lot about hydrogen. Carbon capture and storage is another big one. We talked about those. We are also working a lot on critical minerals. And critical minerals is going to play a very important role in how we transition because you use a lot of critical minerals for batteries. So we do have a large group working on critical minerals. We also have a lot of focus on EVs and development of microgrids to basically transition our current conventional energy system to these renewables. And then we also have focused a lot on what are the land and water impacts of the energy system. So that is under land and water reclamation theme. So it's a very large initiative at the University of Alberta. Now, this brings us kind of very close to the end, and I would like to mention the last one would be more in terms of, recently, University of Alberta was awarded and we set up this NSF Global Center for Sustainable Bioproducts, which is a 6-country initiative. There are more than 10 different universities involved in this. And this is basically focusing on producing sustainable materials because, and we didn't get a chance to talk about this, but sustainable materials are key to transitioning to a low carbon economy. So a lot of focus would be on this. This is being led by US, but we have UK, Japan, South Korea, Finland, and Canada being part of this. So with that, I'd like to conclude this session. Thanks, Matt. And then I would like to thank all the audience. I would say that, with this event, there are many more events are happening throughout this week at University of Alberta. I would like to draw your particular attention to the screening of the documentary 2040 at the Metro Garneau Cinema on Wednesday evening. We'll be providing expert commentary on the themes of renewable energy raised in the film after the screening. And so check the online program at uab.ca/I week, letter I week, to register for that and all of the International Week activities. So I'd like to thank everybody for attending this, and I hope you are able to attend most of the events for this week. Thank you.